Speak about small particles in Laplacian growth models.
Well, first of all, I'd just like to thank the organisers. It's been a real privilege to participate in this programme. So this work I'm going to talk about is joint work with Frederick Wicklund and Alan Solar, who's in the audience, and I'll also speak in some depth about some earlier results that I have with James Norris. So just a brief overview. So I'll start off with a pictorial motivation, which is really just an excuse to show everyone some pretty pictures. Then I'll give an overview of the Hastings-Levertov planar random growth models. I'll summarize the results for the simplest case of the model, which we call HL0. I'll then introduce the regularized Hastings-Levertov growth model, and finally I'll end with the scaling limit results that we have for this regularized model. So what are we trying to do with random growth models? Well, we're trying to describe clusters of particles that grow through random aggregation by essentially you attach new particles to the outside using some sort of random attachment rule. So this picture is probably well known to quite a lot of you now. So this is diffusion limited aggregation, which models the physical process that you get. For example, if you have an electrode in a copper sulfate solution, the positive ions randomly diffuse around the solution until they hit the cluster, at which point they stick to it. And you can see the sort of clusters that we get here. They're very sort of fractally, and they get sort of a lot of long thin fingers. Here's a second picture. So it's a little bit difficult to see this one, but this is a holiday picture actually I took in Utah a couple of years ago. So this is a sandstone paving slab, and on the paving slab you can see there's a sort of fern-like structure. It looks a little bit like a fossilized fern, and in fact they're actually called pseudofossils, but they're formed by manganese in the sand, so it diffuses around before the sandstone was actually formed. And again, formed one of these sort of aggregation patterns demonstrating, so again, with sort of dendrites and sort of fingers growing. A different type of growth model that you can get is the Eden model, which describes biological growth. So here things are a little bit different. Instead of particles coming in from outside and sticking on it, you have a cluster of cells, and the cells on the boundary of the cluster can reproduce at a certain rate if they have a space in which to reproduce, and so you can see what we get here is a much rounder, smoother shaped cluster, but again it still has these sort of random fluctuations in the edge, which are actually on quite a large scale. Just two more pictures. This is what happens if a lightning strikes an object. Charges sort of bounce from the lightning strike across the surface of the object, and in this case, lightning striking a pavement, you can see the sort of scar left behind. And again, we get some cluster that grows because of some random rule. And last picture, just because I like this picture. So this, I guess, unlucky chap over here has been struck by lightning. The lightning sort of struck him in the shoulder there, and the lightning strike exited at this point. And exactly the same as on the pavement, the lightning charges sort of bounced across his back and left him with this sort of rather attractive electrical tattoo that's marked there. So this is really the motivation for studying these growth models. Is we're trying to in some sense model and understand physical processes, and in particular we're trying to understand why we might be getting these random branches forming. Why we don't just always get always sort of get very smooth growth. Okay, so the Hastings-Levertov construction, this is a family of models proposed by Hastings and Levertov in 1998, and it's a very rich family of clusters, family of models, and it covers all of the examples that we've described already. So diffusion limited aggregation, dielectric breakdown, and the Eden model for biological cell growth. And in this particular family of models, clusters are formed by iteratively composing conformal mappings, and each composition corresponds to the attachment of another particle. And what we're primarily interested in is the asymptotic behavior of the large clusters, And it's natural to consider cases where the particle sizes are very, very small compared with the overall size of the cluster. So we're trying to sort of picture things where the particles are sort of on an atomic scale and we're looking at macroscopic clusters. And so we take scaling limits where the particle diameters tend to 0, while the number of particles grows at a rate that tends to infinity. Okay, so to explain the Hastings-Levertov construction, first of all, we need we need some idea of what a single particle corresponds to. And so if we just let d naught be the exterior of the unit disk, and so P will, sorry, starting to see where David was struggling this morning. So, and P is going to note a particle attached at the point 1. And for most of our results, they're fairly universal, that we can take particles to be sort of any sort of shape as long as it satisfies certain conditions. Symmetric helps, and it shouldn't be too flat. But for the purpose of simulations and for some of our finer results, we take the particle P to just be a slit of length d. And in this case, we can explicitly write down the conformal mapping that goes from the exterior of the unit disk to the exterior of the unit disk without this particle. So when we use Fp, we mean any particle P, but for certain results, we'll explicitly use our particle to be a slit. Okay, so once we've got a single particle, how do we construct our cluster? Well, it helps if I draw a picture to illustrate this process. So just to, first of all, display a bit of notation, we say that the size of a particle is d if it has diameter d, and we say it has attachment angle theta if theta lies in the closure of the particle P. So supposing now we have a sequence of angles P1, so a sequence of particles P1, P2, etc., and that to each particle we know what its diameter is and we know what its attachment angle is. So we iteratively construct our cluster in this way. We start off just with the identity map, and then recursively, supposing that we have a mapping phi n minus 1, which goes from the exterior of the unit disk to the exterior of some cluster with n minus 1 particles. Okay, so now we want to attach our nth particle. So how do we do this? Well, we know we have a mapping corresponding exactly to the nth particle. So we have a mapping Fn, which essentially takes the exterior of this unit disk to the exterior of the unit disk without a particle at a certain position. Then what happens is if we then compose with our mapping corresponding to this cluster, what does it do to this red particle? Well, it maps it onto something that's attached onto the cluster boundary, because the whole unit disk maps onto this white cluster boundary, and so it puts our particle Pn into this position over here. And so what we have now on the right hand side, we have a cluster which now has n particles, because we had the n minus 1 represented by the white cluster, and we've attached one more particle over there. And so we can actually just go directly from the exterior unit of the disk to the exterior of this cluster without that particle, and so that gives us a mapping phi n, which is equal to phi n minus 1 composed with Fn. And so recursively, that gives us a sequence of mappings, and each mapping corresponds to increasing compact sets, which we call clusters. So here's just a simulation, just with a small number of particles arriving, and you can see a certain amount of distortion takes place. So this was the first particle, then this one came in, and later particles sort of get stretched by this mapping. So what is this shape over here? Well, this is exactly phi n minus 1 of Pn, where the Pn represents that set over there. So there's a certain amount of distortion that takes place, and I'll talk about that in a bit more detail. But the main feature, you can see that we in this way we can describe increasing compact sets. Okay, so we've got a lot of flexibility and freedom in these models. Particularly, we can choose the sequence of angles theta in any way that we like, and we can also choose the particle sizes dj in any way that we like. And for every sequence of angles and sequence of slit lengths or particle sizes, we generate a new physical realization of a cluster. So what are natural choices of these angles theta n and the sizes dn? So if we think back to the motivational pictures that I showed, the DLA model is the one to sort of bear in mind, which is particles are diffusing in randomly, and they attach at the point that they hit. So in this picture, the place where we want to attach the next particle wants to be distributed according to harmonic measure along this cluster boundary. So what's that going to correspond to in this picture? Well, we can just take the pre-image of this conformal mapping, and because it's conformal, it preserves harmonic measure, and harmonic measure on the unit disk is just the corresponding to the hitting distribution of a Brownian motion is just the uniform distribution. So if we just pick an angle uniformly on the unit disk to attach our particle, that will exactly correspond to the hitting distribution of a Brownian motion on this irregular shaped cluster. So that suggests that choosing our angles theta n to be IID uniform random angles is a very, very natural choice to use. Okay, so what about the slit lengths or particle sizes? What are natural choices in that case? Well, again, being guided by the trying to model DLA, in this picture, we really want to be attaching particles that are roughly all the same size. Well, what's the size of this particle here? Remember, we've got phi n minus 1 of Pn over there. Well, just a very, very crude calculation says that the size of this, or the diameter of this, is approximately the derivative at the attachment point. So phi prime n minus 1 of e to the I theta n times the size of the particle Pn, so times dn, which was the size of the particle Pn. Okay, so if we want this to always give us something roughly the same size, always equal to something roughly like d, we want to choose dn to be close to d divided by phi n minus 1 prime at e to the I theta n. So that's a sort of a rough way of choosing our angles in such a way that in this picture the particles are roughly the same size. And what Hastings and Nevertov did, they went one step further and they introduced a parameter alpha in such that they chose the diameters to be the derivative of that, the power of alpha over 2. And so you can see here choosing alpha equals 2 does recover our heuristic DLA type model. And they argue again heuristically that choosing alpha equals 1 corresponds to the Eden model, and in fact taking values between 1 and 2 correspond to the dielectric breakdown family of models. So one of the problems with their model is if you just look at the form of this, it's complicated primarily for two reasons. So the first complication comes from the fact that in order to know what size to make our jth particle, we need to know this map phi j minus 1, which depends on all of the angles theta 1 up to theta j minus 1. So there's a really, really long range dependency taking place here. So we haven't got any sort of, for instance, this process dj is not at all Markovian. And a second problem is the derivative of this map is evaluated on the cluster boundary, and typically conformal mappings are quite badly behaved on the cluster boundary. So these models, although we can write them down and simulate from them, they're actually very, very difficult to study. There's one exception which is easier to study, and that's if alpha is equal to 0. Then we just have dj equal to d, and at that point the maps, the particle sizes are all, so the particles are all IID, so the mappings to FP are all IID, and we have a Markovian structure that we can recover. So this case alpha equals 0, even though it doesn't describe any physical clusters. In fact, we can show the distortions that you get stretch the particles exponentially. It is mathematically the most tractable, and a detailed study was carried out by together with James Norris in 2012. Okay, so I'll just show some simulations of what these Hastings-Levertov clusters look like. So this is a simulation of HL0, and so you can see it grows roughly like a ball. And here's the one that we're really interested in, HL2. This is the candidate for DLA. You can see this one really is exhibiting this sort of dendrite growth, sort of long fingers growing and sort of fractal type looking arms. Okay, so I'll just summarize some of the results that we have on HL0 together with James. Okay, so just a bit of notation. We just let C be the logarithmic capacity corresponding to the a single particle mapping, and for the slit, there's an exact relation between the capacity and the slit size. So roughly, the capacity is like the slit size squared over 4. And so our first result about the HL0 cluster is about the macroscopic shape. And what we say is if we look at the map phi n that takes the exterior of the unit disk to the exterior of the cluster with n particles, this approaches the mapping e to the cn z as d goes to 0, provided that n doesn't get too big, but actually we can have it getting really quite big. And geometrically what this means is that the cluster after n arrivals approximates a ball of radius e to the cn, and actually we're able to do an even finer analysis that tells us that the nth particle is located very, very close to e to the cn plus I theta. So what you can think of happening is, as the particles arrive, we really just blow up like a ball. When we have a new particle arriving, we have an angle corresponding to that, and you can just think of that particle just coming straight in on that angle and just sitting on the boundary of the cluster, roughly where that angle is. Okay, so here's some pictures just to illustrate the scaling limit. So what I've done here is I've used different colors for different epochs of arrival. So in the first epoch we've got red ones, and the pink ones come in last. And here you can really see that we do get the sort of quite big distortions happening with the particles. So this is just with particles of size 0.1 after 800 arrivals. Then I go for particle size of 0.02 after 5,000 arrivals, and then I shrink my particles even more, and I go for 20,000 arrivals with d equals 0.02. So if I just run through that again, what you can see is happening is we really are filling out and converging into a disk, and there really is very little penetration going on here. Pink particles won't make it into the blue region. There's a little bit of penetration just along the edges, but in the limit, this really is just going to grow like an expanding disk. Okay, so in that sense, some sense, these results on the surface can seem a little bit disappointing, because all we've been able to show is that the most expected behaviors taken place, that we have an isotropic model, and it's given us the obvious isotropic limit in 2 dimensions. But there's actually something a little bit more going on in this picture, and you can see it best probably in this picture here, that every particle has a notion of ancestry. So when a particle arrives, it attaches to a parent particle, and that in turn was attached to a parent particle. And so you can trace these ancestral lines all the way back down to the unit disk, and this creates a sort of internal tree-like structure. And I'm pleased to be able to mention that word, so I can tie this in with the theme of this workshop. And so somehow this idea of just viewing the limit as an expanding disk misses this internal ancestral structure that's going on the inside. And so there's actually a more detailed analysis that we can do to try and understand what's going on with this tree-like genealogical structure. Okay, so in order to understand this, we need something that we call the harmonic measure flow. And so what in order to construct this flow, we need the inverse mappings of our clusters. So supposing I have a cluster again with n particles, and what I want to know is how much harmonic measure grew between these 2 points. What is the weight of the harmonic measure inside that? Because that somehow is going to tell me when the next particle comes in where it's going to attach itself. Is it going to attach itself? Is its ancestral line going to end up somewhere in this arc or somewhere else? And so if I take the inverse mapping, gamma n, which is phi n inverse, that maps to the exterior of the unit disk. Well, what happens to these 2 points? Well, they were on the cluster boundary, so they must still be on the cluster boundary. And because of the conformal properties of these mappings, the harmonic measure of the whole cluster between these 2 points is exactly the harmonic measure of the boundary between these 2 points, and this is just exactly given by the difference in the angles between here. And so, roughly speaking, you can think of the harmonic measure flow as being a sort of lifting of the restriction of this mapping to the cluster boundary, the lifting onto the unit circle. And we don't have to just define harmonic measure just for our mappings that go from the unit disk to the nth cluster. We can actually run our cluster up to a certain point m, and then run it from m further onto n, and that gives us a harmonic measure flow between times m and n, and it satisfies a sort of weak flow property, which is where the name comes from. Okay, so how does this harmonic measure flow behave under successive arrivals of particles? Well, okay, well, let's just take a single point on the cluster boundary and just think about what happens when the first particle arrives. So supposing our first particle arrives, and then we have a mapping phi 1 inverse, or gamma 1, let's just call it gamma 1, and that takes this boundary to the unit disk, and so this slit has sort of been unzipped and become this red part of the boundary. Well, what's happened to our point x over there? Well, it's moved to a new point over here, gamma 1 of x. Okay, now supposing another particle arrives. So supposing it arrives over there. Now we have a mapping gamma 2. Well, what's gamma 2 going to do? Well, that's going to sort of probably shrink this red arc a little bit and insert the blue stick somewhere into the cluster boundary down here. And that's going to have the effect of moving this point x a little bit that way to gamma 2 of x. And if let's just do one more particle, if a third one arrives, and supposing it arrives attached onto the red one, well, what's happening there? Well, now we need to unzip inside this red bit of the arc. So we end up with a red bit there, and the contribution from the green bit is over there. And once again, now under gamma 3, this point now hops a little bit to the other direction. So every time a particle comes, this jump here this point here is going to take some jump corresponding to composing with the inverse mapping, and because we're in the alpha equals 0 case, each of these jumps is going to be IID, because the jump is only determined by the map corresponding to the ith particle. And so it's not hard to believe that in the limit, as we let our particle size go to 0, that corresponds to these jumps getting smaller and smaller and smaller. They're IID, and so in an appropriately chosen scaling limit, you can believe that this point will track a Brownian motion on the unit disk. Okay, what about if we had 2 points? So let's start this picture again. Okay, let's take 2 points just somewhere on the cluster boundary. And supposing a particle arrives over there. Well, for this limit, you need to remember that we're in the limit as the particle sizes get very, very small. So this particle is small, and it's going to get zipped into the cluster cluster boundary. And as it does that, it's going to give this point a little nudge that way. But because it's very, very small, it has a very local effect, and so this point over here doesn't see that. So it isn't going to really move. If instead a particle arrived over here, then as it gets zipped in, it gives this point a little bit of a nudge in one direction, but this one doesn't really feel it. And if we had a particle arriving somewhere far away from both of them, as it gets zipped in, neither of them will really feel that. So each point really in the limit only feels the particles that are arriving near it, and so again, heuristically, you can believe that the motions tracked by these 2 points are going to be independent as long as they stay far apart from each other. So we've now got 2 independent Brownian motions being tracked on the boundary of the circle in the limit as the particle size goes to 0. So there's just one more case we need to consider, and that's what if the points are very, very close to each other. Okay, so here are the 2 points that we want to track now under the harmonic measure flow. So suppose our first particle comes in. As I said, if it lands anywhere around here, it doesn't affect either of them, so we just need to worry about ones that land near these 2 points. So supposing our particle comes in on that side, well, this is going to get zipped into the boundary over here, and that's going to give each of these points a nudge that way. Similarly, if we had a particle arriving over there on that side, that gets zipped into the cluster boundary, and it gives each of these points a nudge this way. So there's only one more case. What if something lands between the 2? Well, in that case, it's going to sort of tear them apart and nudge the left one to the left-hand side and the right one to the right-hand side. But if they're very, very close to each other, that's an extremely unlikely event. So almost all of the particles coming in are going to nudge these 2 points in the same direction. And so again, heuristically, you can believe that what we've got here is independent Brownian motions on the unit disk, on the boundary of the unit disk, until they meet, at which point they track each other or they coalesce. And I've just done this for 2 points, but we could do it for, we can take any sequence of points around the unit disk, and again they perform independent Brownian motions under this harmonic measure flow until they meet, in which case they coalesce. Okay, and this we have as a theorem. So what the precise result says that if we speed up our process so that our particles arrive at a rate which depends on the particle in a way that scales with the particle size like d to the minus 3, then the harmonic measure flow can be shown to converge to the coalescing Brownian flow, which is also known as the Brownian web on the circle. And so if you have n points on the unit circle, so let's go back to this picture over here. So let's just take n points on the unit circle, and what we want to know is as the cluster grows, how does the harmonic measure grow between each adjacent pair of these points? Well, our result says that if we just take n coalescing Brownian motions, which are starting off at these points x1 up to xn, then the harmonic measure between each consecutive point evolves like the difference between these coalescing Brownian motions on the circle. Okay, and here's a simulation. So what I've done here is I've just put, I think I put 100 points on the unit circle, and I just looked at what happened to those points under successive arrivals of the particles. And so as you can see, for any particular point, if we track its angle, so we've lifted this to the unit interval. If we just track what's happening to each point on the boundary, it performs a Brownian motion, But if you look at 2 points, they perform independent Brownian motions until they meet, and then they coalesce. So what does that tell us about the harmonic measure? So for instance, the harmonic measure between these 2 points on the boundary, at that point it becomes 0, and so that means that the cluster in some sense has grown around whatever was started getting rooted between those points, and so no particles can actually get in. The probability of particles actually getting in there, anyone contributing to that is 0. But in addition to the coalescences, we have these points of bifurcation that necessarily have to be there, and so the points of bifurcation, or the gaps that form, tell you that these are the places where we're getting a lot of growth happening. So just this little point sort of down here on the cluster boundary now has a huge amount of harmonic measure growing there. So that means that the branches growing there are now really taking over quite a big proportion of the cluster, and a lot of the later reproduction is going to result in this guy as a sort of common ancestor. So as you can see, this harmonic measure flow has very, very close connection to the sort of ancestral properties, or the tree properties of the cluster. So just to make that more precise, the exact relationship, what it helps to do is sort of just sort of take the logarithm of our space. So we define k and tilde to be the points whose exponential lie in our cluster, and then for every point with positive real part, we can define a finger from that point to be that we take the nearest point in k and tilde, so the nearest point in the sort of log of the cluster, together with all of its parent particles. And we can also define a gap path to be the minimal path from the nearest point not in the cluster to infinity that doesn't actually enter the cluster. So this is just a schematic diagram to illustrate that. So as I said, I've taken logarithms, so this is a periodic picture, and these little disks just represent particles in the cluster. Again, it's just a schematic, so in practice these will be quite distorted. They won't all look like little disks. So let's take a point W that actually lies in the cluster. What's the finger from W? Well, it's the particle containing W together with all of its parent particles right down to the imaginary axis, which corresponds to the unit circle. How about this point Z? This one's not in the cluster, so we need to find the nearest point in the cluster, and we take the parent, we take the particle of that corresponding to that point together with all of its parents. So this is the finger corresponding to Z, and with the gaps for this point Z, you can imagine attaching a piece of string to Z and sort of tugging it from infinity, but in such a way it can't enter the cluster. So you can see it takes the shortest path it can to the outside, but it can't actually go inside the cluster. And for this point W that is actually in the cluster, we take the nearest point outside the cluster, so that's over there. We attach a piece of string to that, and we give it a tug. And again, because it's periodic, the gap path is this one over here. And so what you can see with these fingers and gap paths, again you have some coalescent properties going on. So fingers will coalesce if they have a common ancestor, and gap paths sort of in the limit sort of coalesce if they're sort of both forced through the same sort of gap. So points from here will potentially coalesce from points from there if they're sufficiently constrained. Okay, so what is what we were able to prove involving these fingers and gap paths? Well, we were able to prove a global limit result, which basically said that if we just fix some capital T, and we let n be cd to the minus 1 times t. So remember, c is like d squared. So this is roughly looking on a time of order d to the 3. Then, if you remember our shape result, which told us that at that time, at time n, we have a disk of approximately size a radius e to the cn. That means that we've now got a radius of size e to the t divided by d. So in d small, we're talking really, really big clusters that we've got at this point. And what our result says is that if we now look at this k and tilde, this logarithm of this cluster, and just take a finite set of points, we can ask for that finite set of points, what are the gap paths and what are the fingers, and our result says that the gap paths correspond to coalescing periodic Brownian motions starting from E, and the fingers correspond to coalescing backwards Brownian motions starting from E. So again, this is probably best seen in a picture. So what I've done in this picture is I've taken a finite set of points, and for each point I've generated coalescing Brownian motions going forwards and the dual coalescing Brownian motions going backwards, and then I've sort of exponentiated the whole picture to turn it back into a disk. And so if we take this point over here, our limit result tells us that the finger is very, very close to this blue path, this backwards coalescing Brownian motion heading towards the disk, and the gap path is very close to this pale blue path going backwards. And with this picture, I think the way to think about it is a little bit like with Wilfred's pictures yesterday. Is the real cluster is completely filled in. That's what our limit result told us, that the limit is a dense disk. So what we've really done here is we're just taking a sample of fingers and gaps from that disk, and so this finger going down here follows a Brownian motion. The gap path to the outside follows a pale blue Brownian motion, and what that tells us is that, remember, the blue path is the shortest distance to the outside, and so for the shortest distance to be this really wiggly Brownian motion, that must mean that there must be parts of the cluster coming arbitrarily close to that path. So if you can try and sort of fill in the gaps mentally to see what's going on. Okay, so how can we interpret this in terms of ancestry? Well, if we just look at the outside of the boundary, and we ask ourselves about who's the common ancestor of this point here, well, we trace its finger path all the way down to the center. We can do that with this one as well. We trace its finger path down, and you can see these two finger paths coalesce at that point. So that means that everything that's growing in this arc is going to share the same common ancestor. Carrying on a little bit, you can see again between these two paths, these ones all coalesce at that point, so everything on this arc is going to share the same common ancestor. And in fact, because these paths are sort of given by exponentiated coalescing Brownian motions on the circle, we know that if you run coalescing Brownian motions on the circle for long enough, eventually they're all going to coalesce into a single Brownian motion. That means that if we look for long enough, if we let this ball grow enough, and we trace back the ancestral lines, they're all going to go back to a single point on the original unit disk. And you can really see it's happening to a fairly sort of dramatic extent here. All of these points between there and there already have a common ancestor over there, and things are getting sort of closer and closer packed in. So unfortunately, you can't see the exact common ancestor in this picture. It's all sort of compressed into the middle there. But our results about Brownian motion tell us that there is just a unique common ancestor coming from this picture. Okay, so if we compare that sort of picture to for instance, our ideas of DLA, where you seem to be getting several different arms forming, it sort of starts asking, well, there are obviously some alphas where simulations suggest that we no longer have a single infinite branch, and so you might ask, what is the smallest value of alpha for which HL alpha has more than one infinite branch? And we're going to give a partial answer to this question. And the reason it's a partial answer is because we need to move to a regularized model. We haven't been able to say anything for HL alpha with alpha strictly greater than 0, but we can say quite a lot about a regularized version of HL alpha with alpha strictly greater than 0. Okay, so how do we construct our regularized version? Well, we need one more parameter sigma. Once again, we just take the theta j's to be independent, uniform, random variables. But this time we pick the capacities according to this formula. So if you remember again, capacities like the square of diameters. So if you take the square root of this, you get a formula that's very, very similar to the Hastings-Levertov formula. The only difference is that we have a sigma here where Hastings-Levertov had a 0. So setting sigma equals 0 here essentially recovers the original Hastings-Levertov models. Setting sigma equals infinity here just makes this the capacity, and so we can show that actually setting sigma equals infinity, you get a deterministic sequence of diameters whose capacities to leading order are given by this formula over here. So we now have a bigger family of models where sigma equals 0 is what we have before, and sigma equals infinity is something that we can understand relatively easily. So what does this regularization give us? Well, we still have the complicated long-range dependencies that the original Hastings-Levertov had. We're still depending on our derivative of our phi map, which still depends on all of the angular attachments. So we still have that complication, but we no longer have this problem that we're right on the cluster boundary where the derivative's really badly behaved. So that's giving us some control over how much these capacities or these diameters can change, and so that makes it easier to control the long range, the effects of the long range dependencies that exist. Okay, so here are just some simulations. This is a HL2 cluster with regularization parameter 1, and you can see once again we seem to be getting a disk similar to the HL0 case, but instead of our disk sort of growing exponentially fast, we can show here that actually it's growing in a way that preserves the area growth per unit time. And what if we go for a slightly smaller regularization? So this time we've regularized by sigma equals 0.02, and now you can see we actually are recovering the sort of interesting sort of finger-like like pictures that we expect from DLA. So a regularization, if it's strong, does tend to throw away the interesting behavior, but it does keep some of the average physical behavior that you expect. But this sort of suggests that if we take our regularization small enough, we really can still get interesting anisotropic limits coming out. Okay, so what are the results we can say for our regularized model? So let Cn star be the capacity corresponding to sigma equals infinity. So that's the exact form that we get if we take sigma equals infinity. And what we're able to show is that if we let sigma, it can tend to 0, just not too fast. Then we can show that the actual capacity converges to the Cn star capacity, this deterministic capacity, in a sort of logarithmic sense as C goes to 0. And I should just say this condition that sigma tends to 0 but not too fast, some condition like that has to be here, because as I showed you, if we let sigma get sufficiently small, we start getting really anisotropic pictures coming out of it. But this somehow is stronger than we really feel we should have. We feel that the results should be true for sigma up to some sort of c to the power of some gamma. So unfortunately, we haven't been able to sort of relax that condition. But I think this bit should be possible to relax. Okay, so what will this allow us to do? If we can show that our capacity sequence in some sense behaves deterministically, then we can import all of the techniques that we had for HL0, and that allows us to sort of, using some coupling argument, and understand our regularized models. Okay, so here's just a simulation of the capacity sequences plotted against time, and you can see that there does seem to be some very strong deterministic behavior going on here, just very, very small fluctuations against the deterministic capacity sequence that you would expect. Okay, so by using our coupling argument, we can get very, very similar results to those that we got for HL0. So first of all, we get a macroscopic shape theorem that tells us that the map corresponding to n particles looks like 1 plus alpha Cn to the power of 1 over alpha to the z, or geometrically, our cluster looks like a disk of radius 1 plus alpha Cn to the 1 over alpha. And if you notice here, if you let alpha tend to 0, this gives us the exponential of Cn, so we recover this HL0 result. What about the harmonic measure flow? Again, we can get similar convergence results to the harmonic measure flow, but in this case, we have a number of different situations that can arise. So once again, we need to rescale the harmonic measure flow to d to the minus 3, or capacity to the minus 3 over 2. And one of three things can happen. So depending on how alpha relates to our particle size. So if alpha tends to 0 faster than the particle size, then the limit of the harmonic measure flow is just the coalescing Brownian flow on the circle with a certain diffusivity. And really, we recover exactly the same result as with alpha equals 0. The diffusivity is just because for these results we're using slits. But aside, so that I don't get sort of worried about that. Really, we have exactly the same result here that we do for HL0. I'll do this case next. If we don't let alpha tend to 0, or we just let alpha tend to 0 very slowly, in such a way that alpha over d tends to infinity, then the limit is the identity. And what that means is that the harmonic measure flow just doesn't really change. And the picture to have in mind is somehow a cluster that, oops, sorry about that. Somehow a cluster that just grows like this. The harmonic measure between any 2 points just stays roughly constant as the cluster grows out. So the ancestors of particles in a certain arc are going to sort of correspond to points in the sort of shrunken arc on the original circle. So in some sense, if you ask how many common ancestors are in this picture, well, arbitrarily many ancestors as you let the limit get finer and finer and finer. So what's the intermediate case? What happens if we choose alpha to tend to 0 just at the right rate, which is it tends to 0 exactly this, as a constant a times the slit length? Well, what happens then is that the harmonic measure flow converges to a time change of the coalescing Brownian flow on the circle, and this is the important bit, stopped at some point, and we can write down the time change explicitly. Okay, so let's see some pictures of that. So this is with alpha being very small. So alpha. So here you can see this really is just coalescing Brownian motions. The diffusivity doesn't really seem to change as we go along, and we get a picture very similar to the alpha equals 0 situation. So at some point, these 2 points are going to coalesce, and supposing that they coalesce that way, that will mean that this point over here is the common ancestor for all later arrivals. So so here you can see we're really not very different from for alpha equals 0. What about if we let alpha tend to 0 at the same sort of rate as c? So here we've just put alpha equals the square root of c. Then you can see that the diffusivity really seems to be slowing down. So here we've got some quite fast sort of Brownian behavior, and it sort of gets slower and slower. And so you can imagine, I mean, some of these will probably coalesce, but as it's getting grounded to a halt and getting slower and slower, you know, maybe you know these three will survive, and that will tell you that that you have a few different common ancestors. So possibly that common ancestor can survive, and this one down here might survive, and maybe that one as well. So we really have a different situation taking place here. And so the thing we really want to know is, well, how many ancestors are going to survive in that situation? So in other words, how many gaps are we going to have at the end of this process? And because this is just a time change of a stopped Brownian motion, that means we want to know how many gaps we have at the stopping time of that Brownian motion, and it's a deterministic stopping time. So for this, we use this very beautiful result of Bertoine and Legal, which relates the Brownian web or coalescing Brownian motions to Kingman's coalescent. So what it says is, if we just take p uniform points on the unit circle, and we start coalescing Brownian motions from each of those points with a particular diffusion coefficient. Again, that's just chosen just to make the rates work out. Then we can define a partition on the unit circle given by given by those Brownian paths in much the same way that I've explained over here. So at this particular time point, here's our partition. You can just go down and see which bits of the unit circle are connected. And so what the result says is that the partition process that we get at time t is exactly given by Kingman's coalescent. And Kingman's coalescent has been very well studied, and so this allows us to import the results about Kingman's coalescent to try and understand the distribution of common ancestors in our random growth models. Okay, so here's the exact statement of what we can say. So once again, we just need this technical condition that sort of sigma tends to 0, but not too quickly, and we just concentrate on this case when alpha c to minus half tends to a for some a between 0 and infinity. So as I said, if it tends to infinity, we're just in this situation where we can have arbitrarily many common ancestors. So that in some sense isn't such an interesting case. Okay, so if we let capital B be the number of common ancestors in the limit as the particle size tends to 0, what can happen? Well, if a is equal to 0, so we just get one common ancestor almost surely. So we're in the HL0 case. If alpha is strictly greater than 0, if we let Tj, so tau j, be the time of coalescence into j partitions of Kingman's coalescent, then we can write down the property distribution of the number of common ancestors in terms of the property distribution of this time tau j from Kingman's coalescent, and this value a. And in particular, you can see that the distribution is stochastically increasing in A. So we started with the alpha equals 0 case where we have one common ancestor, and then we very quickly, as alpha goes from being 0 to taking macroscopic values that don't depend on D, we take a random number we can have a random number of ancestors in such a way that's stochastically increasing up until we get to this point when alpha is macroscopic, where we can get arbitrarily large number of ancestors. And then just importing the results about Kingman's coalescent, we explicitly know what the distribution of tau j is. It has the same distribution as the tail of a sum of independent exponential random variables with rates at k choose 2. And furthermore, conditional on having exactly j common ancestors, we might want to know, well, what's the distribution of ancestors on the unit disk? Well, it's exactly the position of j independent uniform points on 0 up to 2 pi. Okay, so just to sort of summarize these results, so supposing that sigma tends to 0 but not too fast, then in the limit as c tends to 0, the cluster is a disk, but the internal structure, we have one of three possibilities. We can have a single infinite branch if alpha tends to 0 much faster than the diameter, a random number of infinite branches whose distribution is stochastically increasing in A if we tune the rate that A tends to 0 to be exactly matched with the particle size, and deterministic radial growth if A is much bigger than the diameter. Okay, and then I'll just finish with just some references. So this is the paper of Bertoine and Legal, which shows this relationship between the coalescing Brownian motions and Kingman's coalescent. This is the original paper of Hastings and Levertov, where they proposed their model, and then this paper is a paper on the regularized model with Frederick Vickland and Alan Solar, and this is the paper with James Norris where we look at HL0. Okay, so thank you.
Yeah, there's a regularization, but do the heuristics apply with zero regularization? Does it tell you that this should be how it behaves, even though you can't prove it?
So you mean the heuristics about about our results that we have here?
Yeah, the heuristic behind.
Yes. So those seem to not need the regularization. So there seems to be a phase transition that happens at alpha equals 1. So if you look at the clusters that you get as alpha goes from 0 up to 1, they all seem to grow like disks. And then as you go from 1 up to 2, you start to be getting cusps and fingers growing. And heuristically, it seems that all of our results should hold for alpha between 0 and 1. So as long as we're getting the disks, it doesn't seem to be that bothered by the regularization. It's sort of close enough at what we're getting. What's happening very close to the cluster boundary doesn't seem to change that quickly. When alpha gets bigger than 1, then the whole thing's changing. So I mean, the simulations are suggesting we can't get disks, and so we really do expect our results to break down at that point. And likewise, this idea of deterministic capacities. I mean, that really breaks down as well. So, I mean, what actually happens with the regularization? If I just go back to this picture. So if we just take alpha less than 1, what happens as we let sigma get 0? This gets fatter and fatter and fatter, but it still seems to have this sort of deterministic average behavior. Whereas when alpha's bigger than 2, we just get something completely unrecognizable. Over here, the whole thing just breaks down. So and somehow it's this capacity sequence which gives us our results. So heuristically, they should hold when alpha's less than 1, but there's, they're not going to be even true when alpha's bigger than 1 if our simulations are to be believed.
Other question? Maybe I need something with heuristic for alpha is equal to 1. You said that it corresponds to the Eden model.
That's right. Yeah.
Why?
So this is something that's in the original paper by Hastings and Levertov, and they really just get it by comparing growth, by getting growth rates. So, I mean, we have a small amount of additional evidence that actually the growth rate argument is maybe not too far off. Which is if you look at this result that we get for our regularized model, if alpha is equal to 1, what we're getting here is it's a ball of radius 1 plus cn, and so that means that the circumference is growing at constant rate, and somehow this is something that you would expect from an Eden type model, that the circumference should be growing at constant rate. So that sort of seems to tie in that if any model corresponded to Eden, it would have to be that one. But the fact that there's some model that corresponds to Eden is just a heuristic.
There is no other question. Then let's thanks Amanda again.